Hi everyone. So let's finish up what we were doing last time. And just before I move on to the definition of min, which I'm just going to throw up a couple of versions of it, here's a cleaned up example of what the min factor code could look like, what I was scratching down with a pen last time around. Now, technically, what else could I have done with this particular code? Well, does it necessarily have to be just an int? How about unsigned int? Gned. Oh, I can't spell English. Bad. All right, so there you go. Unsigned int, and you would also do an unsigned int right here, which would mean you don't have to worry about cases of negatives. Potentially, that's what you might want to have for if I was changing my function around. If I was going to clean up my function the next iteration, I want to point out again that when you're writing code, oftentimes you might be wrong the first time. You might not have it perfect. That's fine. It's an iterative process. Nothing comes out perfectly immaculate the first time. So that's why we doodle on a piece of paper, and that's why we actually think, we might do one pass and then might clean it up again later. We refactor our code, meaning to clean it up or to move things around but not change the behavior. So we're going to look at the min function, then I'm going to go over some more C code. After this little mini lecture, then we're going to go to actually live coding up what linked lists look like. And then we'll see, and that we're going to keep on using linked lists, which is a data structure that we're going to look at. We're going to use linked lists for the rest of term as sort of the demonstrating example for all the various topics we're going to do. Okay, and so we can also look at a real world example, and we can actually look at the code itself. The real world example will probably come next lecture. So here are three different solutions that came from previous terms. Uh, Notice I should have that indented slightly. There we go. Right? The formatting does make a difference in terms of readability. This is being written up in PowerPoint, so it doesn't automatically format the right way. But if you're writing it in Visual Studio and the formatting looks wrong, it means there's probably something wrong with your code. Right? You may have a syntax error, and you can go find it fairly easily. You should not be fighting against the compiler, the IDE, when you're writing your code. If you are fighting against it, it either means your style is wrong or you have something wrong with your code. Fix that first, right? You shouldn't be having to manually put in spaces and the like. It should automatically happen. So let's look at the three different versions that we have of this same code. And as I said, the code is relatively easy. It is a function called min that takes in two parameters that was I implicit. I think I said maybe they said they were integers, but they could have been anything. They could be floating point numbers. We just had to be consistent. They took in two integers. That's our input, and it spits out. Our output is right here. It spits out an integer. So it's going to take those two numbers, and it's going to return one or the other. And what should we be able to guarantee? We should be able to guarantee it's either going to be X or it's going to be Y, no other number. There's no negative one, there's no errors, anything like that. The minimum of two numbers is going to be one or the other. Those are the options. That's it. So a lot of times people were giving me doing print out statements, getting the answer from the user if you were trying that. If you didn't try this exercise, by the way, shame on you. Really, seriously, if you don't, not seriously, shame on you, but seriously, if you're not doing the exercises while we're talking about them, you're going to have a hell of a time later. You will not know when you're confused unless you actually do a lot of these things. So, if you cannot do that function, now is the time to ask questions to get help, to figure out what you're doing wrong, because you need to get up to speed really quickly. Okay, here's our min function. It's going to return one or the other, either the value for x or the value for y. That's what a function does. It has two values going in, it spits out a value at the end. So I could have some return value. So a lot of people would be doing like printf statements and getting scanfs and getting things from the user. I wasn't asking for that. I was saying, you pass me two numbers, you tell me which one's the smaller number. You don't have to print anything out. You're returning a value. Print statements outputting to the screen is the rarity. It's the exception, not the rule for functions. Most functions just handle numbers and deal with numbers. Sign doesn't print something to the screen, it resolves to some value. Here in this case, I can make a temporary variable called retval. I could then see if x is less than y, I set retval. Otherwise, I set retval to y. So whichever one's smaller, if y is smaller than x, y is smaller or equal to x, we make retval equal to y. Otherwise, we make retval equal to x, and we return retval. That's all well and good. Notice I had a lot of people give me errors. I don't know how. Well, I do know how, but think about it for a second. When I sort of bring it up, they're giving me errors when x is equal to y. And I go, why? Why would you put an error message for that? If you're telling me what's the minimum, 4 or 4, the answer is 4. You don't have to give me an error message. The minimum value of those two numbers is 4. Pick or choose whichever one you want to return. They're the same value. It's not an error. If you give me -1 and 4, like, can these values be negative? Absolutely they can. Can they be 0? Absolutely they can. Can they be really ridiculously big? Sure. It's just whatever the smallest of those two numbers is. And if the two numbers are the same, you return whichever number you want. They're the same number after all. So a lot of people jumped into code and wanting to do error messages and stuff like that without thinking through and like, what's the human understandable version of this? If you tell me to give you the minimum of two numbers and they're the same number, what would you say? You would say that number. What comes before August 24th or August 24th? Well, August 24th, right? It's the same number, right? It's the same date. So here is, that was one version of min. Here's another, the more streamlined version of it. Notice they are all going to be effectively equivalent to each other. They're just slightly less code in some of these cases. So instead of making a variable and then returning the variable at the end, I can just get out of the program as soon as I hit this scenario. As soon as I know which one to return, is x less than y? Yes, it is. Okay, just return x. Otherwise, just return y. That does the exact same thing as the code before. These are two different implementations. They do the same thing. One is slightly better than the other one. There's less code to read. It's a bit less clunky, if you will, and I don't have to make a new variable. Okay, but it's not the end of the world. You'd get a right answer for both of these cases on an exam. Here is how I would end up doing this, and this is purely because I did too much game development a long time ago. Else statements used to be slower when they compiled, and you can get into the ooey gooey details of all of that. The else statement used to be a branch misprediction when you compiled it, and essentially would slow down your code a little tiny bit. Not anything anyone noticed unless you're talking about a game loop where you're pushing out a lot of polygons or a lot of voxels or whatever you're doing. In my case, sprites. So instead of using an else, I could just say return. If this is the case, return. Otherwise, by default, I have an else condition, and so I just return y. Though again, those two are exactly the same to each other. You have a style to coding when you code something, and there's, by the way, a little bit less line. It's a little bit less robust and or a little bit less verbose. That's the word I'm looking for, than the other solutions. But they're all fine. Just because you didn't do it one particular way doesn't mean it's wrong. But if you have your function that says return 5 and then return 7, you did it wrong. Right? It should be your inputs can be anything you want. You figure out which one's bigger, you return that value. That's what it had to be. That's what the question was asking for. And if you didn't do that, you got to seriously think about why you had that problem and look for help. Because this class is going to get a lot faster. Okay. So, at a glance, what other things have we not dealt with? Well, we have iteration. So we have different kinds of loops. One of them would be like a definite loop, or defined a certain number of times. So a for loop would be a classic example of this. It is going to do exactly 5 iterations. Why? Because it goes from 0 to less than, not less than and equals, but just strictly less than 5. So it goes 0, 1, 2, 3, 4. That's 5 different numbers. 0, 1, 2. I'm counting with my fingers here, by the way. 0, 1, 2, 3, 4. 5 numbers. Which is why we do our if for loops looking like this. Starting at 0, the first element in our array is position 0. The last element in our array is the size of the array -1. It just works wonderfully for arrays. So I don't even think about my for loops. They always look like that. And what's the next letter after? If I have a for loop within a for loop, what is the letter I'm using? Is it I? What's the letter I use? Hopefully many of you know what the answer is. It's J. Then it would be K. And I don't think I've ever gone to L, right? You that is by convention. You might think, hey, that's a bad name, but I, J, and K. If someone sees I, J, or K in your program, you think it's a for loop. Every programmer looks at it and says that's a for loop, and that's the counter. That's the index for where they are in the array by convention. Just like X, Y, and Z are coordinates in space, three-dimensional space. So that's a for loop. A while loop, you might have a certain number of conditions. You may know when it ends, but not necessarily. A while loop is I will keep looping while this thing is true. Until this thing is false, I will keep looping. So here's a while loop. And we have some kind of condition. While, and let's say I is less than 5. Let's actually intentionally screw this up. Int I is equal to 0. While I is less than 5. And then do something. Do the same thing as in here. Why am I saying I'm intentionally screwing this up? Because I'm going to start I is equal to 0. And then within my while loop, if I do not change the value for I is equal to 0. 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 I have an infinite loop suddenly. That's an indefinite. It doesn't have to be infinite, but an indefinite loop is you don't know when it's going to stop or if it's going to stop. I can make this into a definite loop by just doing this. I plus plus. It's definitely going to stop. It will eventually get to 5 and it'll stop. So these two loops are now identical to each other. So these are the exact same thing now. One's done with a while loop, one's done with a for loop. And you should be comfortable with making a for loop. We have also decision making. We've done this before. We did it right here. If and else statements. We also have an else if, which looks exactly like an if, but it says else if instead. That's the only difference, right? And it just means I go in this branch if this is true. I go in this branch if this is true. It allows me to go to different branches. A switch statement looks something like this. So switch. And I'll have, let's say, character C. Or some value. We have some value here. It has to be something. I have to hit the nail on the head. Well, there are new ways of doing this that I still have to figure out for a switch statement where you can do ranges. But for the most part, do this. And normally we would have the word break in there, meaning if the character I'm dealing with, C, well, let's call it a better name than C because we have all these A, B's, and C's here. So switch my char. The variable that I'm using called my char. Okay, if my char is equal to A, do this. If my char is equal to B, do this. If I don't have a break in my case, I will automatically go to the next case, the next case, the next case, the next case. I will automatically just keep on flowing down. I won't jump back out automatically. I only jump out when I hit that break statement. So if my char is equal to A, I will do whatever's for the A condition, then I will do the B condition, then I will hit the break, then I'll get out. And oftentimes we have one more part of this, which is, and you can look up all of these things yourself. This is just meant as a refresher. Oftentimes we will have a default condition. If I don't know, none of those other cases are true, I go into the default case. Switch statements are not all that used that often, but they're used fairly frequently. We also had, I guess, what other thing we had was we had these sort of inline conditions as well. But we don't need to go into. We'll hit those when we need them. Okay. So what kind of problems do you normally have? Well, first of all, many times, just par for the course. If you forget something, or you rate your header wrong, what library you're using, if you forget to include something, if you spell it wrong, whatever the case is, you get these cascading errors. If you have an error at the very top of your program, you get a million one errors along the way. So that's one of the first things when you're debugging something. If you have, compilation errors, go to the very first compilation error, maybe go to the very top of your file just to make sure you have no errors there. But also go to the very first compilation error. Number two, the most common thing that for people, they forget semicolons. They put them in the wrong place when they do have them, and they forget them when they do need them. It normally indicates the end of a line of a separate sentence. So my for loop doesn't have a semicolon at the end, but a some kind of assignment, for example. Let's go back here. Here we go. Semicolon here. At the end of a line, I have a semicolon, right? But I don't have it at the end of my if statement because the if statement goes from here all the way to here. So that is one giant statement, and you can string them all together. But end of a sort of a semantically complete or a unit of operation, something that you're doing, that if else statement sort of works as one thing. This is, I'm going to return this one value. I have a semicolon at the end. So unless I have the curly braces, normally got a semicolon there. And it's something that's a very common error. Oftentimes missing curly braces, the matching curly brace. It used to be much, much worse in the bad old days when you had to actually count your curly braces to find out where those ended. Things are a lot easier now, but hopefully not that bad. This is a big one because people wonder what the heck that is. And I normally pose the question, what's the difference between single equals and double equals? So let you come up to the answer for that one. What's the difference between those two? They are very different. This is assignment. The single equals means assignment. It means, whatever's on the left-hand side, give it whatever the value is on the right-hand side. So if I have int I is equal to 4, I give the value 4 to I. This thing here is a test for equality. Is the stuff on the left-hand side equal to the stuff on the right-hand side? So I could have, let's not move my screen. I'm going to say idx or int. Bad pen. For index. Assignment. Condition. Right? If this is true, then do this. Clearly, it's not going to ever be true. You're never going to do what's ever inside of here. That stuff here is dead code. But that's what your test. This is a test for equality. This is an assignment. Okay. If you're missing the and before scanf, we're not going to have to do that for very much longer. What does that and do? If anyone remembers 1400. That and makes it a pointer to the variable rather than the actual value of the variable. And so when we look at scanf in a couple more examples, that's a very common mistake that people make all the time. In a similar vein to the equalities versus equality versus assignment, we have single and double and they are different as well. This one here is this condition and that condition. It's a propositional logic thing. It is if this is true and this is true, then the whole thing is true. This single and is a bitwise and, as in the and if we can deal with bitwise operations in a second. It means if all the bits are the same in some of those places, if a number on one side and the number on the other side, or the binary representation on the left hand side and the binary representation on the right hand side, there is some place where there have one in both positions, it will be true. We can look at that in later, but for the time being, you don't see that very often. For if you wanted a double equals, you should not be using a single equals. Uh, and my big problem always, and it bites you in the ass in way worse than all these other cases, is when you run your program, run and you compile and run your program at the same time. Now, some people suggest that you should, but I disagree. The reason I disagree is for a very important reason. Often people turn off the flag saying, hey, there's a compilation error. So they turn off that and they go to compile and run all the time as one unit. And so what ends up happening is you compiled your code correctly, you have working code, you make some changes, then you're trying to compile it again, but it's broken. What you then run ends up being the old working code, not the new code that you're making changes to. So you can keep on running your code, trying to figure out what's going wrong, and nothing changes in your code. You can get these weird cases where you're working on code for like 2 hours and you cannot see why nothing has changed in your code. You made these radical changes to your code and nothing shows up. And the problem is you have a compilation error somewhere. You're not even looking at your new code. You're testing the code that you wrote 4 hours ago. If you don't have a separate step of compiling and then running, you don't catch when you have a compilation error. And you need to know when it doesn't compile, because otherwise you're not testing the right code. That's a common thing for 1400 and 2400. So compile, then run. Don't do it at the same time. Otherwise, you will find out the hard way after spending a couple hours, and then you'll be like, oh, I shouldn't have done that. Okay. But you won't do it. You won't think it's an important thing until you hit this scenario, like I have several times. You won't realize it's a problem until you hit this scenario. All right. For me, there are some really quick, hopefully quick, uh, ideas at a glance. So, for good practices, I always think before I code. So I break down the problem before I actually write up the code. I always make sure I have proper indentation so I can read it and other people can read it, because in 6 months' time, I have no idea what I just wrote. Heck, in 2 weeks' time, you won't know what you wrote or why you wrote it. It's also why you put comments. It's for the TAs, it's for you, it's for making everyone's life easier. You would never in a million years, like if you wrote a math problem and you just cranked down a number and dropped down a number, you didn't put any of your workings in there, it would be considered wrong, but no one would be able to figure out what you were trying to do. And if you had a mistake in there, you'd not be able to trace why you have a mistake. The comments save you. They allow you as a human to read what the heck you were trying to do 2 weeks earlier when you forgot, and since you've since forgotten. Um, do never ask for just you know some number. Like if you have a prompt and there's nothing to say, hey, put in this number, which lots of people do. It's faster to not put a printf statement in there. And then so you happen to have to know that you have to enter a number there, right? You just get you're supposed to type in a number, but if you don't get told, hey, type in a number, the next person to use your program doesn't know that they have to type in a number. Um, People have a tendency of just cramming in everything into one gigantic function. So you have these monstrous functions. Oftentimes the main method. Oh, good God, get your code out of the main method, right? You shove everything into the main method, and you have a lot of repetitive code, and it's huge, and you cannot figure anything out. Breaking big problems into small little chunks and putting those chunks into different functions is extremely useful. We have more lectures on that as well. Please use very meaningful variable names. If you name your variables A, B, and C, you should lose points. IJK, it better be indexes, right? It better be some position in my for loop. Try and come up with a good variable name. And if you come up with a crappy one, like a really crappy one, you should lose points because other people have to use your code. You should definitely be always testing your code every single time. Figure out what the weird cases are. You know, I'm trying to sort a list. Well, what if the list is empty? Well, what if the array is empty, right? You need to care about all the situations where you may not have thought about, all the weird situations. That's a mark of a great coder, is to figure out where things could possibly go wrong. Uh, and in similar name to breaking functions into smaller ones, if we want to they're highly related. When you get too many functions, you break out your code into separate modules, into separate files. We will also be doing that. It makes a lot more sense to do that once we do object-oriented programming. Instead of having one file with 5,000 lines of code, which by the way is not that much, instead of one file with 5,000 lines of code, you have 5 files with 1,000 lines of code, right? If you can break apart big monstrous things from one behemoth file to a whole bunch of little parts, it can make your life a lot easier, especially if you organize your code in a meaningful way. And so, in case you're wondering what I mean by bad formatting, you can have a pause the video if you want to read this comment. It took a lot of it hurt to try and write this, but if you want me to read it out here, let me try it. Do you think the badly do you think of badly formatted text? I mean, it's not like it matters. I mean, seriously, you can all read this. So, and there's a footnote, it takes practice. Bad formatting will cost you points. And two, please format code correctly. Right? If you give me badly formatted code, your TA will not be able to read your code. And they are not just testing whether it runs. They are looking at the code and making sure it's in the right format. Because, quite frankly, whether it runs or not is irrelevant. Other people have to read your code later. You have to read your code later. Get in the habit of formatting it correctly. Okay, so in terms of the easiest, most effective practice that you can have, bring a notepad and pen. That is 90% of the problems. And I keep on having students go, I don't get programming. And they come and they're very upset, and they're concerned about their ability to do code, to program something. And I don't get this. And I go, okay, can you walk me through it? And they start coding. I'm like, what are you doing? And they're like, I'm coding. I didn't ask you to code. We're working through the problem. So yeah, I'm going to code it. No, get your fingers away from the keyboard, get a notepad, get some pen, get something lightweight that you can play around with and doodle. For people that did my Viz class, you know very well that I hate just trying to write a formalized visualization just off the top of your head. It's going to be wrong. Nobody does things right the first time. You scratch, you doodle, you figure it out, and then you implement it properly. And so pen and paper is your friend. If you don't know how to do something, or a whiteboard, whatever it takes, have that around you. On your exam, you should have a pen and paper right next to your computer so that you can doodle something around and figure it out before you start writing your answer. It doesn't take long, and it'll save you far more time in the long run. It is ridiculous the amount of cost savings you do by just playing around with a pen and paper. If it's your least bit confusing, doodle something, make sure it's right, then code. Seriously. Okay. And as a quick reminder, just for those that are, I know that some of you are going to, flog yourself anytime anything doesn't work. I love just the switch of mentality here. A novice programmer gets really excited when they got it right running the first time. And an experienced programmer expects failure. And this is not hyperbole. This is actually everyone. There's something that goes seriously wrong. When I'm going to live code for you soon, if I don't get a compilation error, I will be freaked out. I will not know what to do, and I will be like, okay, something terrible happened just then. I must have something wrong with my code, even more wrong with my code. Because compilation errors are human nature. If you're writing at a certain speed, you're going to do something a little bit wrong. There's always something wrong. The question is, what is your expectation? Your expectation is you're going to get some minor errors, you're going to fix them up, you're fine. Any error is not the end of the world. They're expected. If you expect perfection the first time, you're going to be sorely disappointed. If you're public speaking, because I'm just doing this right now, if you're public speaking and you think every single word out of your mouth is going to be golden and perfect and, no stammers, no stutters, no nothing like that, no random filler in the words like I just did, then you're going to be in for a really rude awakening. Most people cannot write, or compose perfectly formatted words without any kind of script, without any kind of ums and ahs in it. It's the expectation. But a lot of when you're novice, you expect to not have any ums and ahs, or maybe you expect to say things perfectly the first time. Not going to happen. Just stop flogging yourself and expect to have to fix your code. This also leads to another major point that we're going to get to, which is do a little bit, test. Do a little bit, test. Because if you expect problems, doing a little bit and fixing it means you're going to, in the long run, you're going to save yourself a lot of time. You don't do the entire house and then test to see if things work. You don't build some large structure and then test to see if it's going to work. Bit by bit, as you're building something, you want to be able to test along the way. So, for me, my first thing is pseudocode first. That's why I have the pen and paper, right? These are my coding survival tips. And by the way, for 1400 especially, but even in 2400, asking for pseudocode is a valid exam question. It also forces you to try and think it through before coding. Do not just code. And somebody that's listening here will try. And I apologize in advance, but that's your fault, right? You're going to get to the exam, you're going to just try and code something without having thought it through, and it's going to bite you in the ass, and then you're going to be like, oh, okay. If you have enough, self-reflection, you'll go, oh yeah, that's why he said do pseudocode first. It's not formal. It's just thinking through the problem. If it's steps on a journey, you want to do a little bit, test, a little bit, test, a little bit, test. You don't want to move on to the next step until you know the first one is working. You don't just throw random crap together in an IKEA bookshelf and then you put it up and hope to God it holds together. You do one part, make sure it's right, then you check to make sure you did it right. Move on to the next part. Put your comments in there because you don't know if you're going to understand what your code was doing in the future. Honest to God, it happens all the time. Uh, you want to think about all the weird edge cases. What happens if this thing values a negative? What happens if it's zero? What happens if I pass in a string that's an empty string? Right? You want to think of all the unexpected results, come up with weird edge cases, and be able to test them ideally. If you have something, you can't do everything all at once. The Tim Hortons pseudocode is from 1400 in case you're for paying a cashier. But if it's something like sort the array, that's a hard task to do. So maybe you just say, I'm not going to sort the array right now. I'm going to put literally the words to do in a comment in my code. Don't sort the array yet. Finish up what other thing you're going to do and then come back to it later. You can do that as long as you know that you've marked that you have to go back to it. So sometimes you can't do everything all at once. So you say, I'm going to do that later, finish off what I'm doing, come back to it later. And for the time being, it should give the wrong result, and then later on you can fix it. This is what's called test-driven development. It is huge in industry. It is sort of the standard approach for most people, for most programmers. You write your tests, then you write your code, then you make your tests pass. If you write your test first, which also relates to this, if you write your tests first, you're not writing the test to pass the code. You are seeing you're seeing what you expect success is, and then making the code pass that. It's also what we have for learning outcomes in this course, by the way. We have a learning outcome, and then I write the lectures based on the learning outcomes, not the other way around. Because I could easily make a lecture and then make learning outcomes based on the lecture, but that I may not be testing the right thing for what you need out of this course. If you have an error at the beginning, it will cause errors later. So people panic when they get 400 errors. Fix the first error, recompile. Fix the next error, recompile. Start at the top, one by one, fix each code error one after the other until you're done. And every time you fix an error, recompile. Because that first error could cause 400 errors. You may only have one error and then you have 400 errors. It's saying you have 400 compilation errors because you made one mistake at the very top of your file. Like missing curly braces will screw up your entire code afterwards. One bad pre-compilation header piece of information, like one bad define, will screw up everything afterwards. If you do it in a methodical way, you can fix your problems. If you guess and just start hoping to fix random bugs in there, you'll make more bugs as a result. So methodically, start at the top, go to the bottom. If you're trying to figure out what's going on, so printf statements can be your workaround. So asserts also work, but if you're really, really stuck, throw in a printf statement, see what you get from the result. If you put in a printf statement that you know should go off and you don't see a printf statement, there is something else going on in your code. Maybe you have a compilation error, you're not seeing it, and therefore you're seeing it looking at an old version of your code, right? These are your job is to sort of iteratively deduce what's wrong with your code. That's what debugging is. The only way you get good at debugging is with practice. I cannot teach most of it. It comes with experience and staying relatively calm while you're trying to debug something. And it's a pain in the ass, and everyone goes through it. So, in case you're panicking over it, it's fine. That is part, it's going through the salt mines. It's the pain in the ass that is coding. But it's so gratifying when it finally works, which is why we do it. We go through all this pain just for that. When it finally works, it's the greatest feeling in the world. Okay, if you don't know where something is, what's going on with it, throw in a breakpoint. I love breakpoints. You can also do a cert. Breakpoints are different. So you can pause your code at a particular line by, well, we'll show you examples of that if you haven't seen that before. It is clicking on sort of on the left-hand side of your code, and you'll be able to drop a breakpoint. So it looks like a red stop sign. And when your code gets to that line of code, it'll stop, and you can look at what the values are in your code, and you can figure out why things work the way they do. And that's why you need to know hex, by the way, from 1400, because you need to be able to read that code and know what's going on. So here is a simple C program. It is I just have a main method. I have a couple includes, standard IO, and we're going to define some message, hello world, with a new line afterwards. Notice if I screwed up something along with this thing here, I'd have 10 errors just for one error up here. Okay, so what does this thing do? Here's my actual code. I will print this message. What is this? This is a hot, sort of a find and replace. Everywhere you see you see MSG. This is actually what's being put in the code. The hello world /n. It's hello world /n here. So printf hello world /n. Just it's being done without your knowledge what's going on. Then I'm going to set a variable I, and I'm going to set it equals 0, and then I'm going to return I. So I'm going to return 0 at the end. Okay, that's a fairly easy piece of code. But again, if you're having any particular problems with your code and you're getting a bunch of compilation errors, you want to start at the top and work your way down. We're going to have to do arrays, a lot of array stuff, and we're going to look at arrays and structures next. This is where their 1400 knowledge goes awry. It's like pointers, arrays, and structs. So what is an array? It is, well, you could say it's a group of variables of the same type. Okay, so it's a bunch of integers. But really, it's a big chunk of memory. That's all it is. It's a chunk of memory that holds, 10 integers. So that's, it's 32 bits per integer, and the standard is 320 bits. You access it by going through an index, so you can jump to any position in the array. So our array looks like array position 0, 1, 2, 3. The size of the array is 4. The positions are 0, 1, 2, 3. Why? Because we can't count? No, it's because it makes the math easier if we start counting at 0. So always we're doing 0-based indexes. Okay, so that's an array. That's a fairly simple array. We'll also do with structs. And a struct is a bunch of data, but they could be different types of data. They don't have to be the same type. They can have different names, and it's essentially duct taping a bunch of variables together at once. So we will look at an example in a second, but this is a contiguous chunk. They're both contiguous chunks of data, but this thing up here, this array, is a contiguous chunk of the same data type, and you can just jump around in it. And this down here is, I got a bunch of different variables just sort of taped together. So I would like you to take out yet another piece of paper. We're going to pause after this. I want you to find an array in an index, find a particular value in an array. So we're going to have a value we're going to look for. The name of the variable is going to be to find. So this is parameter 1. Here is parameter 2. Notice this is a pointer to an array because that's how our arrays, when we're passing arrays to a function, that's how they work. Here's the name of my array right here. It's find in array. And I'm going to have a third variable, which is the size of the array. And if anyone knows Python or any of these other languages that are a bit newer than C or in C++, you may, why the hell do you need to pass that in? Because C just has a chunk of data and a pointer to the front of it. It has no idea how many elements there are, how big this thing is. It has no ability to get that information. As a result, you can't say you can't just get the size from the array. You have to pass that as another variable because you have no idea how big that array is. I just know I have an array of integers. How big is it? No clue. That's what that third parameter is for. This function that you're going to write is going to return the index of where that value is. And if that index is not found, we're going to return -1. Now that's by convention, right? We could return, size, right? That would also be not a legitimate number here, but we need some number that is not a legitimate thing, because if you return 0, that's the first element. If you return 1, it's the second element in your array. You need some element that cannot be in your array, some number that cannot be in your array as your return value. And so in our case, we're going to return -1. If we can't find it, we return -1. Okay, so I want you to pause the video now, try to write up that function. I have the answers for it. Make sure you're comfortable with writing that function and how it actually would be called and how it would work. Okay, so hopefully we're back. Hopefully you actually did it. Let's actually look at this function. So here is how my code could look. Here I'm making an array called numList, a very original name, that takes in 5 parameters, 5 values: 5, -2, 3, 8, and 5. I'm then going to call find in list. I'm going to look for the value 3, and here's my passing in the array here, and the size of my array, 5. I'm then going to go find in list for 4, which is something that's not in my array. The value 4 is nowhere in here. Here's numList, here's the size of my array. So what would I expect find index to be when it stops? And what would I expect find index 2 to be when it stops? So what I would expect is I'm going to walk through this thing. When I find a 3, I'm going to stop. So 0, 1, 2. I would expect this. I expect this to be the value 2. 0, 1, 2. That's where the 3 is located. And when the 4 is not in the array at all, so it goes 0, 1, 2, 3, 4, and it should return -1 if it can't be found. That's what I expect from my values. I haven't written any code at all yet. I get a piece of paper, I play around with it, I see what I would expect this thing to behave like. This is the same as you do with a math. If you're doing a math proof, I never start with a proof. I play around with some numbers, make sure I get a sense and a feeling for what the question is, then I try the proof, right? I want to get a sense of what this thing is going to do, then I try. Okay, so here would be one version of find in list, right? It takes in, here's the thing it's trying to find, here is the array it's looking through, same thing as this, it's this thing here. So this is 5, -2, 3, 8, 5. This value I'm looking for is, for the first case, is the value 4. And in this case, this number here, size, is equal to 5 right here. I'm just going to do a for loop. Now, do I need to check to see if the value is less than 5? Well, no. I can just start at my very first element and go onto the end of my array. And if I find what I'm looking for, I get out immediately. So I'm going to start at position 0. I'm going to go up to but not including the size of something. So 0, 1, 2, 3, 4, and then I stop. When I is equal to 5, I would stop. And every time I increase I. So is the thing I'm looking for 3 equal to 5? No. Is 3 equal, no, next time around. Is 3 equal to -2? No. Next time around. Is 3 equal to 3? Yes, it is. I return whatever my value I is. In this case, the value 2. Great. Okay, and I would be done with that function call. Next time I call find in list with 4, now I'm listing 5. So I'm looking for 4. So let's put some of these in there. 4, this is 5, -2, 3, 8, 5. This value is 5. All right, so I'm looking at startup position 0. Is it what I'm looking for? No. Move on. Look for the next one. Is it what I'm looking for? No. Move on. Is 4 equal to 3? No. Move on. Is 4 equal to 8? No. Move on. 4 equal to 5? No. Move on. I is equal to 5. I is equal to 5 now. So I've had I is equal from I is equal to 4 to I is equal to 5. I is equal to 5. My for loop stops. I go down to here, and then I'm returning this value here. I'm returning -1, and I'm done. That would be me finding an element in my array. This should not be overly crazy for you guys, but I just want to make sure we're on the same page. Okay, so when we come back soon, what I'm going to do is we're going to look at pointers and structures. I probably look at functions again, and then what we're going to do very, very soon is we're going to look at a linked list. I'm going to implement a linked list as a bunch of structures and the like, and we're going to keep on revisiting linked lists throughout the term. Just wanted to give you guys advance warning. All the code that we're going to be dealing with is going to be on a Google Drive. I will make sure that that Drive link is available to you on CU Learn. So we have a Google Drive link, and all the code that I write for all these lectures will just be there. So you don't have to frantically write anything down. You always have access to any code that I write in the class. Normally I'd even live code it. You could even see it being live coded. In this case, you have to wait a little bit. But you will always have opportunity to get the code that I write in one of these lectures in this Google Drive folder that I'm going to share with you. So when we come back, we're going to look at pointers and structures a bit more, and then we're going to deal with linked lists, bringing it all together, hopefully, and give a sense of what we're trying to do. Okay,